Welcome back, guys. Today's question is all elements into binary search tree. In this question, we'll be given two binary search trees and we have to form an answer which will contain the elements from both the binary search trees in a sorted order. So the output would look like this. First will be 20, then it will be 23, then it will be 39 probably, yeah, 39, 41, then 43. So yeah, something like that. And at the end it will be 70. We know that in-order traversal of a binary search tree gives us the sorted list, right? So we can, let's try to find out the in-order traversal of both the binary search trees. So for this search, binary search tree, it will be 20, 23, 39, 43, 45 and 70. And for this, it will be 41, 49, 50 and 61. So now what we can do is we can merge these two lists by comparing every element and we can form the final answer. But forming these two lists results in some extra spaces, right? So how can we optimize it? How can we minimize the space? Let's see. So we are traversing both the trees separately, right? To optimize the space, we can traverse both the trees at the same time. How can we do that? Rather than traversing recursively for the in-order traversal, we can traverse both the trees in a single loop while maintaining a stack. And that stack will have the average space complexity as O of h rather than O of n, where h is height of the tree and n is number of nodes in the tree. So now let's just run through the algorithm. We'll have pointers pointing to the root of both the BSTs. We'll have stack for both the BSTs for the in-order traversal. I'll name it as S1 and S2. We'll have the output list, which will return at the end. Yes. We'll push 45 and we'll check if 45 has a left child. Then we'll move the pointer to 39 and we'll push 39. Then we'll check if 39 has a left child. So we'll push 20 after moving the pointer to 20 and then we'll check if 29 has the left child or not. So it doesn't have a left child, so we'll stop there. And for this BST, we'll push 49, then we'll move the pointer here, then we'll push 41 and then we'll stop because this doesn't have a left child. So this is basic in-order traversal. And after that, when we stop, we'll check if from the top of the BST, which is the smallest element, 20 or 41. So 20 is the smallest. So we'll push 20 into the output list. And after pushing it, we'll remove it from the stack and check if 20 has a right child or not. So we'll push 23 in the stack. Now between 23 and 41, 23 is the smallest. So we'll pop it out from the stack and move 23 to the output list. And 23 doesn't have a right child, so we won't push anything. Between 39 and 41, 39 is the smallest and 39 has a right child, so we'll push 43 in the stack. Between 43 and 41, 41 is the smallest, 41 doesn't have a right child, we'll just remove it between 43 and 49. 43 is less and 43 doesn't have the right child. We'll just remove it. Between 45 and 49. 45 and 49, yeah. 45 is less, we'll push 45 in the output list and remove it from the stack. And 45 has the right child, so we'll push that into the stack. Between 70 and 49, 49 is less, so we'll push 49, and 49 has a right child, so we'll push that into the stack. And between 50 and 70, it's 50. 50 has a right child, we push that into the stack. Between 61 and 70, it's 61. 61 doesn't have a right child, we just remove it from the stack. And 70 is the last element, we'll just add that into the output list. So now let's just go through the code. So this is the structure of tree node. You can have a look at it. In the function, I'll create a list which I'll return at the end. We'll create our both the stacks. We'll create the pointer, which will point to the root of both the BSTs. And then we'll have the logic of in order traversal. So if temp1 is not equal to null, temp2 is not equal to null, and or S1 is not empty or S2 is not empty. Then we'll move the pointer to its left. And in between we'll push the nodes into the stack. We'll do the same for the second pointer. And now we'll check if S2 is empty. And if it's not empty, then we'll check if S1 is not empty. And if S1 S2 both is not empty, then we'll check if S1's top value is less than S2's top value. Then we'll pop from S1's top and we'll push that into this result list. Temp1.val, and we'll move the pointer to its right child. Else we'll do that for the second temporary variable. Yes, so let's test this. Result does not exist. Okay, I spelled it wrong. Okay, so I might have misspelled something. Okay, this should be 0. So it runs. Now let's submit and check. So it's accepted. So thank you for watching. Do like and subscribe. See you next time.